So, today I'll be speaking about tracing, how we implemented it in headhunting. And after my presentation, you'll be able to understand how you could do the tracing in your own situation. To start with, a couple of words about myself. I've been doing the development a little bit more than 10 years, and as Ruslan said, I've been working as an SRE engineer over the past few years. And actually, you can actually ask me questions about how they make beer. Now, about the agenda. First, I'll explain why I needed tracing, which phases we went through in Headhunter, and what additional tools we used on top of tracing. So, as always, I'll start with the overall picture of programs. We have several hundred servers, microservices, more than 3 data centers, and many thousands of applications. So this is the beautiful picture of our microservices interacting. As you understand, it's quite a difficult thing to wrap your head around this picture, to understand what's happening in production. So when you use metrics, traces, and logs, also we add profiling and other tools. But on the whole, how did we usually understand that there was some problem in production? A trigger would fire, and then we would go to logs and see that, let's say, 5 services don't feel good. Maybe a database got down, maybe something exploded in the case, so we had to go deep into the logs. My colleagues, before I joined Headhunter, built log tracing. Let me explain how it used to work. When the request was coming into Nginx, it would generate unique request ID and put it into the header. And then it would pass it to the service as part of the request. The service would get this header, retrieve it, and put into the special logging context. All the rest of the examples will be in Java. Almost all of the backend, in our case, is in Java. So what happened next? The service, because it has already registered this request ID, after that it will also add this request ID together with the log. Then when we pass the request to service 2, we do the same with it. The service would get this and will use this request ID in the log. So all requests regarding this case would carry the same unique ID. Let's take a look how this log collection system was operating. At that point, we had log files on every machine. A file beat would take them, put it to Kafka, and write in the ClickHouse. Now, about reading, we had self-written backend on Python and self-written UI on React. That's how it looked. I guess any logging system now can do that. You just get this request ID, get all the logs on this request, and get it all by service. So on the whole, it's better than nothing, but not too comfortable. At first, we tried to improve the system by adding the tree building based on the timestamp. As you understand, you can't build a fully fledged tree based on timestamp because several requests can run at the same time. And also this tree was sometimes not very good. So what was really wrong about that system? There was no fully fledged request tree, so you couldn't trace the path correctly. And because the UI and the backends were self-written. It wasn't quite comfortable maintaining them. And also the set of functions was quite restricted. For instance, you could do a search only on request ID. You can't do it on method or some additional masks. So in 2020, we decided to do something about that. We took a look at the options we had. So one could choose some open source solutions, some paid solutions, or do something ourselves. We went the open telemetry and Zipkin way. Why did we opt for these? We love all the open source systems and solutions. They can be easily upgraded to solve any problem that you want. Zipkin is written in Java. We were also Javist and thought it's good, and if we're not happy about something, we'll improve that. So there's an asterisk here against the line mature solution. So it was true for Zipkin, but it wasn't so true for OpenTelemetry. They just got spun off of Open Tracing, and some libraries were in alpha or beta versions. On the other hand, there was a CNCF community behind OpenTelemetry, where Google, Twitter, and other good companies are behind. And we decided that the future would belong to them and started to use this version. And also, the developer community was very good, and we thought it would be valuable to borrow experience from them. So let's delve deeper into how it worked. So we had an app. The backends are on Java and Python through special instrumentation. This OpenTelemetry library was written data into the OpenTelemetry agent. Then OpenTelemetry agent would balance the requests among collectors, and then the collectors would be writing into the OpenZipkin backends. I've shown them on the slide in this way because in the process of development, we found out that there was no normal protocol that would support some load balancing. So basically, the authors obviously thought that they needed to use some external load balancer. So at that time we weren't ready to do that, so we built a solution like this. And then Zipkin recommends using Cassandra to store the data. Now let's take a look at how it looked from the client side. On the whole, we took a library from OpenTelemetry, but changed it a bit for ourselves, adding some additional attributes. We've also improved the span export, added patches in order to reduce the load both on the client and the agent. We also add the maximum length of queue because before we did that, we had a few cases of out of span. So memory overflow. So actually, limiting it was a good idea. So let me now remind you that we had this great request ID that we shared between all apps. So it had already been set up, and every app had it in its context. And we thought, why shouldn't we reuse this request ID? By connecting all logs and tracing with the same ID. And again, we did some improvement so that the tracing library should use request ID as a trace ID. In most cases, it did work. So as a result, our first iteration resulted in 3 microservices with some performance, and we started thinking about what to do next. We had problems with Zipkin, that it didn't support the OpenTelemetry OTLP protocol. We wanted to provide for scalability. We didn't have our own hardware, and we wanted to solve this problem in a not too expensive way. And also the storage recommended by Zipkin, Cassandra, was consuming a bit too much resources. So we compared to what we have, and we saw multiple growth of load. We didn't like it either. So next year arrived, and we decided that we needed to choose some other solution. This time, we replaced the Zipkin backend by Jaeger. The reasons for choice were very similar. And again, we wanted to have an open source solution. Of the advantages of Jaeger compared to Zipkin, there was one that it allowed solving us the balancing problem. And also, it was a bit less expensive in terms of hardware. Also, we took a look at where the community was going, and OpenTelemetry was mostly recommending to use Jaeger as a backend. And we decided that it was worthwhile trying. So how did we do? For us, it was actually quite easy. So, because the top three building blocks were not changing, the same protocol was being used to communicate between them, but we threw out the backend together with its storage and inserted a new backend, Jaeger, with Elastic. At the client side, we only changed the UI. Let's see where it ended up. The biggest problem that we solved this way was about balancing. We started spending a little bit less resources, and subjectively, the UI, the Jaeger UI was a bit more user-friendly than Zipkin, but we didn't solve the problem with balancing. As perhaps many other developers, we ended up with sampling. That will perhaps be the only theoretical part of my presentation. What is sampling? If you have a small data array and you only need a small part of it, so this sampling has two algorithms. Algorithm one is called head-based sampling. It works this way. When you get a request at the very beginning, you make a decision whether to store it or not. It can be implemented in different algorithms, it can be random, it can be heuristical, but the essence is that you don't yet know what's going to happen with the request, but decide whether you store it or not. This wasn't a fit for us because we wanted to analyze errors. With head-based sampling, we would have missed most of errors. And we decided, so we didn't like that. And the second kind of sampling is tail-based sampling. It works differently. Here, first, you get the whole request, and after request, you make a decision whether you need to save the trace or not. But you may ask a question of how can one understand? You have hundreds of microservices, and the request goes through like 20 of them, and how can we figure it all out? So here's one option. Imagine application one. It makes its request and sends the trace to the agent. Then the agent, based on the trace ID hash, makes a decision where to send this data. So it's made, it's sent, and the next request goes to the underlying service. It also generates its data with the same trace ID and sends the data to the agent. The agent, based on the same hashing algorithm, makes a decision which collector to send the data in and send the data to the same collector. So this way, all data, however sub-requests would be included, will get to the same collector. And it's clear that the next request will go somewhere else with all this data. Let's see how we configured all of this. So this is a part of our config. on the sampling config. The red here marks the part that's important for us. We see here whether this request had at least a single error, like 500 or above. If there was an error like that, we keep this trace. There are two configs. One is here, and the other option did not find its way here. We are sampling just 100% of all the requests, so that not only erroneous requests should be covered, but all questions. Another good parameter of sampling is decision weight. Imagine a situation. It takes a second to process a request. It's okay, but it may take 30 seconds. And when the request comes, you need to store all the data in one place to make a decision whether it had errors or not after it's done. If the requests are short, let's say not longer than 1 second, it's okay. But if it's a long-running request, as I said, 30 seconds, you'll have to store a lot of data in the collector. So empirically, we arrived at 99.9% falling within 5 seconds. So we made a decision to make a decision whether to keep the request or not after 5 seconds of its receipt. So that was a compromise, a trade-off. So as a result of this iteration, we managed to reduce the load on the database. However, the load on the CPU collector grew because it was keeping data from traces. But on the whole, we were keeping data on 100% of errors with just about 1% of false positives. But then we decided to do something else. So the first thing we did was the error analyzer. So imagine that we have some bad event in production. Users start to get the error messages. So this analyzer fires and it writes to us that problems started, and most of the problems come from this service, and it shows what's the percentage of errors that come from its service. It also analyzes where exactly they originated. It can happen that like an excavator has broken a cable to the data center or whatever. In addition to that, it is showing us examples of specific traces where errors happened, grouping errors by type. Let's take a look at the analyzer algorithm. So roughly once a minute, we get all the traces from the database and count the number of errors that happened in these traces. If we haven't achieved the threshold, we run a more detailed analysis and write the report to the chat, as I showed earlier. If it has, then we do that. If it hasn't, then we wait another minute. Another thing about tracing, the search of endpoints. It's quite a typical controller on Java being added. So you go to the tool, you get some parameter, and you need to understand how it's used in production. Maybe you want to delete it or refactor it. You need to understand where you can touch it. Some people have API systems. We don't have an API system, so one has to find another way to look. What are the options? You can just do a code-based grep. You can, but subtleties can differences may happen. You may search on code. You can do a search on logs. Another option, you can do a search on tracing. And as applied to our solution, the drawback was that we had sampling and we couldn't give a 100% accurate answer that it was exactly this handle that was used somewhere. And you can also use metrics, but we decided that the data cardinality is too high and would require keeping it all for too long. So as a result, we made our choice on the tracing grep. Because it provided the best coverage. Now take a look at the interface of the service. We kind of didn't do the UI. We just built this kind of interface. So what does it give? It shows you from which service you've arrived here, the specific URL. You can also filter by the request type, and it also shows what RPS has come from this service, which may also be useful under refactoring. It's not quite often that we use it in our team, but our architects and developers, when they do refactoring, also believe it a very important feature. Even they wrote their own plugins to be able to see that in their IDE. After some time, and let me remind you that we had this schematic from the application to Jaeger, and we were more or less happy about this. We had it for about 2 years, and over that time we covered everything with tracing. The RPS grew quite a lot, up to more than 600,000 spans per second. And also the scope grew. We started using it for real-time analytics. It was important for us to see downtimes as they were appearing. Also, it was becoming too expensive to scale this whole solution, including both the storage and the collection mechanism. So this time we decided to add ClickHouse and Grafana. The choice was made based on the following criteria, so that it should be open source, but most importantly, ClickHouse provided for quite a stable read time compared to Elastic. And for us, it was important in terms of the downtime analyzer. So again, like in the previous case, we threw out all the backend and installed the Grafana and ClickHouse. Again, the 3 top building blocks were not changing, and then we just replaced the storage system. Let's now look at how it all looked. This is the way that the Grafana trace looked, very similar to Jaeger, and this is an example of a span. What did we do immediately as we got Grafana? Because it's easier customizable than Jaeger, then we immediately built additional dashboards. This one is a dashboard like that. It shows traces on the left and logs on the right. This way, you get a more complete context on demand. Of other additional features that we implemented, we added permanent trace persistence. How does it look? You have some reasonable storage time. Some people have it 2 days, another a week, but there are very few people who keep things for more than 2 months. But it also happens that you found some problem. You would like to save this trace in Jira, but you can't do that because everything will get cleansed. So we built this little vehicle. So when a user comes with a specific trace ID, in addition to going to the database, to ClickHouse, they go to our special history service, which all of it does is actually saving this particular trace. So this way, when Grafana goes to click again, it will. There are two tables there, and it will be able to retrieve the saved trace. Let's now assess what we got in terms of resources. So one backend was replaced by another one. On the whole, it proved beneficial both in terms of resources. The CPU number became twice as little, and other things as well. So based on this experience, we understood that we're spending resources not really on database, but on the collection part. So let's now draw the outcomes of this experience. So our biggest problem was latency, and we put it under control. We made the situation much better. We've also started to spend much less resources. Of the advantages, so we got an interface customization, and thanks to that, we did additional features in Grafana. Of the negatives, we lost the search capabilities that Jaeger was offering. It was very flexible about that. We did not migrate that into Click because after asking the developers, we didn't find any scenarios that required all the capability of Jaeger, and we added only those that were required. And also, as I said, we found out that we were spending too many resources on the collection pipeline. Next year arrived, and we decided to go for some new building blocks. As always, we were trying to make sure it's all open source. Also, benchmark testing showed that it would cost us less in resources. And I can say that when we were trying all these, the address collection vector showed that the vector was a bit on the raw side, but we still decided to go for this. So what the system ended up looking. So here, Open Trace Agent was replaced by Vector, and the collector was being replaced by Kafka. We used to run a sampling on the collector. Kafka doesn't do that. It's used just as a dumb pipe, resending all the data that come to it. So therefore, we started writing all the data from in ClickHouse in this place. That resulted in us having some problems, and I'll share them a bit later. Let's get deeper under the hood. So this is a portion of the config, of the vector config. And while we were doing it, it didn't have a normal way to save the data. One had to convert them from the OTLP format to the one acceptable by ClickHouse. And actually, the transformation was quite big, but it wasn't spending too many resources. Most optimization had to be done on the ClickHouse. And here we were tuning the size of the background pool. And more often than not, we spend on merge file tables. So 32 seemed to be okay. And also we grew the maximum file size, bringing it to 50 gigabytes. And it started working a bit faster. Also, we optimized recording. I forget how much we had initially, but now we have 1 million lines from Kafka being installed. Also, we had to optimize the read function, the read operation, because in Grafana we have certain filters. We tried to speed up search here as well, adding span projection so as to add the search by the required fields. Now let's calculate what we got as a result. Let me remind you that we were replacing these building blocks, collector for Kafka, and we got these numbers.
We saved a lot of CPU resources, RAM grew up, disk grew up significantly. Disk is much cheaper than CPU, so we won in terms of finances. But the main thing out of thousands that we saved, we replaced agent to vectors. It consumes 4 times less resources. Fewer resources we loaded with metrics and resources, and now it weighs the same way as we used before. And now let me finalize this iteration right now. The input RPS is about 24,000 requests per second, 1.2 million per day. We covered HTTP, Kafka, RabbitMQ, JDBC on the request. One of the most valuable acquisitions of tracing was downtime analyzer. It significantly accelerates reaction to incidents which happened in prods and shows us where they took place. It accelerates us, and the engineers are happy too. For developers, the best step forward was endpoints, which simplified refactoring, and we keep 100% of requests. Any request in production we can trace. Minus the drawback, we have much more data, and workload on database is higher. Latency is higher, but it is within reasonable limits. What kind of conclusions can we make? I would make 2. If you don't have tracing at all, please take more or less a ready-made solution based on OpenTelemetry or Jaeger. If you have tracing already, if you have a different solution, a different technology, pay attention to Vector, because it's good, and pay attention to Click, which is much cheaper in terms of resources. That seems to be all. Thank you. Alexander, thank you. Don't forget about QR codes. Vote, provide your feedback, ask your questions into the microphones, and don't forget to introduce yourself. Alexander, hi, I'm Anatoly. My question is, we're looking for Jaeger. But the question is not about Jaeger, it's about business. How long do you store logs in production to solve the problem, to trace the problem? And what is the volume? Logging or tracing? Logs and tracing. Logs. Well, we have 2 options of storage for everything, about 1 month. Maybe a little smaller. It's about 16 terabytes overall. And there is a separate thing for billing. Because of legal requirements, they have to store it eternally. But the amount is small. Tracing, it's about 10 to 12 terabytes. We store them for everyone by default for 2 days. There is another option for tables. they may be stored eternally. Everything is in ClickHouse. Logs in ClickHouse, traces in ClickHouse. And how do you pick up the tables that are stored for a long time or not for a long time? Today, we request a small table. If it doesn't find anything, it goes to the large table. And for Grafana, how difficult it was to tune reports in Grafana. Everything that we did is, we took ready-made dashboard, we added a little bit, added color codes to errors, 500 red, 400 yellow, and it makes it more convenient to look at it from the first glance. All the rest was simple. The only thing which was difficult is in JavaScript to write a piece of code. That's all.
Давайте с другого края начнем тогда еще.
Hi, I'm Artyom. Thanks. The question is as follows. When you stored only the good traces, did you feel any problems? If yes, what was the problem? I didn't quite get the question. What kind of drawback? We store not everything. 1%, well, in general, for incidents, we don't need them at all. 1% to compare good and bad traces is enough. Additional usage, yes, endpoint search. When we have 100% of data, we can say that it is used or not used. This is the only case when we had any problem. Okay, thanks. I am Yaroslav. Thanks. My question is as follows. What do you think about usage LTP protocol for the transport of metrics and logs? The latest version allows us to do so. Good question. We looked at the possibility of sending metrics through this protocol. But let me tell you that historically is so that we use other protocols for that. And we don't see any probability, any reason for doing that. And if we start from scratch, would you use the same? With metrics, yes. With logs, I don't know whether it's good or efficient. I don't have enough information. Yes, they supported it only in the latest release. Thanks for the presentation. Several times we changed the storage and migrated data. Or did you wait until the data becomes obsolete? We used collectors, OpenTelemetry. They allow us to use several backends. And we created 2 backends, and then we turned off one of them. When the collectors were gone, we just used Kafka and disconnected the collectors. For trace ID, you used request ID, and logs were enriched. I didn't quite get you. Logs, request IDs, enriched. We didn't enrich them. Well, we go to 2 ClickHouses, take logs from one ClickHouse, logs from another ClickHouse. How do you correlate data in the context of span ID, not have you got such automatic correlation from span ID? No, we don't. Thanks. I am Dennis. Did I get you right that users were programmers? If so, then did you manage to expand the model, expand it to other departments? And what did they say? I think I got you right. Yes. First of all, we did it for programmers because they were interested most. And then we started using it. Well, we have the operation or sysadmin service. They also use it to collect incidents. As for security department, no, they don't use it. As far as I know, maybe they use it without announcing it, or maybe they don't use it. I don't know. So that side, please. Hi, thank you for the presentation. It was very interesting. And that's my question. For example, in the tracing chain, we have a service which, due to security reason, should not be accessible to the viewers. Did you have such a task, and how can you solve it? Was it out of the box? No, we didn't solve this problem. I think about what kind of data can be sensible for that. We do not store headers and the body of the request. We store only the URL. And of course, theoretically, we might have sensitive data, but usually they are not in the URL. So the answer is no, we didn't do that. And out of the box, I don't know whether we have such solution or not. So for you, it's not relevant. Then, did you use asynchronous operations? For example, service 2 and 3 are not synchronized, but they work through an intermediary. Yes, we had such a problem. We have, through Kafka, integration was done, and sometimes in the best case, in general, even if it comes to Kafka, later it has trace ID and we get it to the database. We don't have sampling and all the data go to the database. There is another problem through Kafka. There are batch requests and we haven't solved this problem yet. Right now, we have this feature. The person is thinking what to do with batch requests, but the problem is yet to be solved. Now, on my left, hi, I am Jaeger. The question is about scalability. You said that you had that problem when you switch to the final stack. Did you solve this problem? Click is not easily scalable. If I got you right, in the latest variation, when we move to Kafka Click, what are we going to do if we need more data? The answer is as follows. Right now, we're dealing with this problem, and the only good option is that hardware. It's not expensive yet, so we are using the hardware solution so far. Now, on my right, I am Maxim. I work in Bison. My question is, in one of the latest slides, you compared the hardware resources. When moving to Vector and Kafka, you needed to have more disks by one order of magnitude. Why so? New data were collected, or Kafka as a broker of messages made you. Kafka stores very little. The main reason is that we turned off sampling. We deleted 95% of cases and store 5%. Now we store 100%. What about Vector? Can you use not sampling, but maybe aggregation? I didn't quite get you. We might do aggregation, but if we store everything, it wouldn't affect us. Then you also said that you store logs in Click. And how do you do that? Are you trying to use full text indices, which Click has? And how do you do that? Let me try to answer at least part of the question. We have two different clicks, one for tracing, the other for logs. Then full text search is not used. We have indices for the most popular fields. And in general, full text search is very rare. And what was the final question? About the data model. But in general, you did answer. So you just pick the most important fields. One micro question. Do you use PS3 for archived data or Click only? Well, for tracing, we don't use any archives. For logs, we are trying to do something, but not yet. Not yet.
Александр, добрый день. Благодарю за доклад.
Hi, thank you for the presentation. I am Fyodor. When you shifted to Click, did you have any problems with sharding and clustering? If yes, what kind of problem and how you solved them? Good question. Well, the simple answer is no. We don't have it. We have three big hardware pieces and three data centers. That's why we don't have problems yet. One colleague asked, how are you going to scale up later? That is a question that will raise up tomorrow when hardware resources will be filled. We shall have to do something. I am Yaroslav again. Thank you for the presentation. I have a new question. What about paranoid tracing, when each piece will be wrapped up with tracing and you have 400 methods, 600 methods in one server? I personally believe that this is excessive, to wrap everything in tracing. On the other hand, I believe it would be nice to wrap them in metrics, not everything, but at least some hot points like entry into the database or sending to a different server. Metrics are much cheaper than tracing, but the usability is as good. Thank you.
Есть еще вопрос.
There is one more question. I will just say thank you. 5-year scope in 5 hours. I cannot hear you well. Well, it's just a thank you. 5-year experience of development was presented in 30 minutes. Thank you. I couldn't hear. It was just a thank. He just thanked you. Thank you for your questions. Now Alexander is going to choose the best question and he will get the book. But you can also get the book through a lottery by leaving your feedback. Please stand up. All those who asked question, it will be easier for us to choose the winner. There was a question about security and whether we filter something or not. There were two questions. Yes, that's I need him. So you have chosen the winner. Thank you.
Спасибо большое.
Thank you very much indeed. If you have more questions, you can ask them offline, off stage.